like we discussed in the second lecture. Okay, so the way those arguments went is that if you have a subset A of the first n integers that lacks your desired configuration, which for us is the nonlinear Roth configuration. Okay, so then in these arguments, you're able to find a long arithmetic progression on which your set has increased density. And then what you do is you look at some rescaled version of the intersection of your set with the long arithmetic progression to get a subset of a shorter interval with larger density that still lacks the configuration you care about. But what happens with the nonlinear Roth configuration is if we have our subset lacking the nonlinear Roth configuration and our arithmetic progression P, on which we have increased density, then now forming the rescaled set A prime. So that's the same, so that's like intersecting A with P, translating it to start at 1 and then like rescaling to fit in the interval from 1 up to n prime. So that's the same as taking the rescaled set to be n such that A plus qn is an element of A intersected with P. So then this rescaled set, so it'll have increased density in this interval from 1 up to n prime, but it will lack, instead of the nonlinear Roth configuration, a different configuration. So it would lack the configuration x plus y, x plus q times y squared. Okay, and now we have a problem that we didn't have before with Charcot's theorem, for example, where the size of q didn't actually really matter. Here it does. So if q is like greater, say, than the length of the whole interval, then actually every subset of the integers from 1 up to n prime lacks that configuration, just on like size grounds for q alone. So then there can't possibly be any leverage to continue the density increment argument. So you're not going to be able to find like anything special about your set saying that it has increased density on some arithmetic progression. So then one cannot continue. The iteration. Okay, and so then the key thing that Sean and I were able to do, okay, I guess key result, is that we were able to obtain a density increment on a long arithmetic progression where q is actually bounded. And then this configuration is similar enough to the original nonlinear Roth configuration that one can iterate the argument. So bounded, by bounded I mean bounded in terms of the density of A. So this will be, yeah, something like this. And still size of n prime tending to infinity with n. Okay, so what we precisely show is, so let's let n be positive, q be some natural number, and we'll set temporarily m to be the square root of n over q. So that should be the range of y for that configuration. So then if A is a subset of the first n integers, and it lacks